Hi everyone, today we're going to go through the scoring guidelines for Unit 2, FRQ number 3, which is the lab-based question from the progress check. First thing I want to do with any lab-based question is to read it really carefully. These problems will often lead you into what kind of data set variables we need, meaning what measured quantities we're going to want to collect in the form of a data table, right? This is a little bit of a trickier, or it may feel a little bit more obscure. In terms of looking at the scoring guidelines, I think it's kind of hard to follow with it, but I'm going to try and clean it up a little bit as best, and hopefully this one is the only one that really feels a lot different as you do other FRQ number 3s from other units. So as we read this very carefully, to paraphrase it, we're going to have a bunch of identical springs. We have different known masses that we can use. Normally this would suggest to vary that mass. You didn't have to in this particular experiment, but you could. And we're going to be trying to verify an equation. Again, normally in these we're calculating some kind of an unknown quantity from an underlying equation like this instead of just simply verifying it. So verifying it leads into a lot of different directions on how you can do that, and the answer key provides a number of different possible solutions. So for those reasons where you might have multiple data sets and you're not really calculating a value with your experiment, an unknown, you're really verifying an equation, then it does feel a little bit more obscure as compared to other FRQ number 3s. So let's take a deeper dive here. First thing we want to do is actually go to part B. So how are we going to collect measurements in the experimental procedure? We first want to figure out like what we're going to be doing, right? And so this is often a good first step. So what we want to be thinking about is, obviously I'm going to be varying the number of springs. So I can do like 1 spring, 2 spring, 3 springs in a series, end to end. So if I look at hanging these to equilibrium, that's a way I can get K. And K is going to be important if we're verifying the K in series versus the K for each individual spring. So I looked at one spring, which is why I have K1 and X1, and the equilibrium position when you hang the mass from it to where it sits at rest, and at that point gravity and the spring force are going to be balanced and can be set equal to each other. So the K value for a single spring is going to be mg over x, and I called this 1 and then substituted in for the K value of each individual spring since they're identical springs. Combining them in series then would be found, the K value for the series combination would be found the exact same way, but we'd have end-to-end springs connected. So it would be mg over x. Obviously, the more springs we have connected, the more stretch we would have x. So if we sub in what the equivalent K value would be, which is mg over x, obviously since it's 1 over that, we would do the reciprocal. So mg over x, that's a data set variable. We're going to have a set of different values as we increase the number of springs that we're using, n. That n is right here. That's the number of springs we have attached. So that'd be like 1, 2, or even 3 springs. So we're going to have 3 different data points here if we use 3 springs. Then my slope here, which would be this 1 over k for 1 spring, would be using that x1 as a measured constant. So that's going to be a constant variable that we determined right out of the gate. As long as we kept the mass the same, then it would divide out and not matter. So I'm going to say here that I'm going to record the distance for 1 spring, which I'm going to call x1. And on a graph, we're going to plot x, which is the stretching distance for whatever number of springs we have, versus 1 over n, where n is the number of springs we have connected in series. If this graph is linear, then our equation is verified, and our slope would be equal to x1, which is mg over k. So now we got to go back and write our experimental procedures. So if we're thinking about it, we need to be hanging a mass from this, measuring that stretching distance x, which we have to make sure is very clearly defined, repeating for a certain number of springs. It's important to note here, we don't have to do any, and we should not do any analysis stuff in part A. We're just going to describe how we're going to collect data. So if we go up to here, we're going to hang 1 spring vertically and place a 0 centimeter mark of a meter stick at the lower end of the spring. We're going to hang a known mass from the spring and measure how far the spring stretches to equilibrium with the meter stick. It's important here, if you don't say the 0 centimeter the mark, we need to make sure it's very clear that we're not measuring the length of the spring, but how far the change in the length is, or how far it's stretched from unstretched, to measure x. As seen in the figure to the left, we're going to connect then a spring end to end with the first spring and repeat step 2 with 2 springs in a series and again for 3 springs in a series. Now whenever I see reduced experimental uncertainty, I'm going to try and make some kind of a comment in there to try and do that. I should note here that the scoring guidelines do not require me to do that. You can see here it is not necessary for the procedure to include a single spring, and although it's good practices, we don't need to perform multiple trials using different masses for each spring combination to earn that point. So I will show you what we would want to put in here if we did want to make sure that we were reducing experimental uncertainty. I always try to say to reduce experimental uncertainty to make sure that the person reading is going to know that I am doing this step to reduce the experimental uncertainty. So we're going to repeat steps 2 and 3, but for a different mass that will create a different data set. And we can use different masses that would each create their own data set. If you did do this step, then you'd have to add to the procedure that you would be plotting each mass's data set as a separate line. Each of those lines would be linear and the equation would be verified. So a little bit of a tricky one there. They're not normally this complicated with multiple data sets and vague rubrics, but this one hopefully makes sense now that we got through it, and we can use this as a learning tool, like an example, instead of beating ourselves up that we're struggling with this a little bit, which I'm sure and I could appreciate I'd see a lot of people here. So going into C and D, completely different experiment, but similar, meaning this one's going to involve springs, but it's a different situation. They're going to describe to you what's happening, give you data, and then you have to do the analysis. So what we always want to do is think F is given, delta X is given, what's my underlying equation? In this case, they give it to us. It's this funky looking equation here. And then we have to create like the linearization of this, meaning like what am I going to plot on my X and Y axis in order to use the slope to calculate an unknown. For example, here they're saying K3 is an unknown, whereas K1 is given. So we got to make sure we read it carefully. If we try to do what makes sense here, given this, which would be to just call F my y-axis, make K3 my slope, plot delta x cubed as my x, and just have the y-intercept as this last term. We can't do this because one of the very important rules that we have to follow here is that you have to have your slope and your y-intercept be constant, which would mean that you cannot have a data set variable like force or delta x, or a data set for those variables. We can't have a data set variable like force or delta x within what we're defining as slope or what we're defining as y-intercept, because that would make them not constant. So anything that's a data set variable needs to reside in the y or x. What's obscure about this problem, again, is that we normally don't have f, which is one data set variable, and the delta x, which is the other data set variable, within the same axis here, but you really kind of have to make this work out in a way that we can linearize pretty easily. So we're allowed to, because notice that K1 is a constant, F is a data set variable, delta X is a data set variable, so we're going to plot that on our y-axis. The slope is the unknown that I'm solving for. There's no data set variables in the slope. Delta X is a data set variable, so we can then put delta X cubed on our x-axis, and we can go ahead and graph this. So I will put down what's supposed to be in my y, what's supposed to be in my x, and then we're going to go ahead and graph those. It should be noted here that we don't actually want to use the line of best fit to get the slope. What we'd like to do is take the data here for what's on our y-axis and the data for what's on our x-axis and create that graph within Desmos and let Desmos run the linear regression and get our slope of the line of best fit. If you struggle on this problem, just remember that you can just plot F versus delta X and earn 3 of these 4 points, right? Because all we need to do is to indicate the appropriate quantities that would be used to produce a straight line graph. We would probably be losing a point on there. In this case, because it's an obscure problem, there may be 2 points, but typically we can earn 2, if not more likely 3 of the 4 points, because if you notice over here, we just need to have a linear graph using half the axis with scales, right? So we need to provide a label and scaling for that and make sure that we're utilizing over half of the axis, the range on those. And then we need to draw an appropriate line of best fit. So it's very typical to these experimental problems where it's not requiring us to earn these points to plot the correct thing. We just have to have the graph labeled correctly, scaled correctly, and just put a line of best fit. That will typically earn you 3 of the 4 points. It looks like in this particular problem, it might only earn you 2 of the 4 points. But regardless, it's good practice to not leave this blank and to try and get those points at least, even if you feel like you're train wrecking the problem and struggling because of this being a weird problem. So using the line of best fit, we're going to get this slope by Desmos, even though I showed visually how this essentially would occur, or how Desmos would be doing it. So we would get the 2.35. And because that is our slope, right, we know that the slope is K3, then 2.35 is K3. I hope this helps. Please let me know if you have questions. I'm happy to go through it one-on-one with you. See ya.